So in this tutorial, there are two things that we will see for the follow-up lecture on the Thursday. One would be doing the normalization, heavy quark field normalization, or the mass normalizations in some sense. And another thing is qualitatively understanding, in the case of bound state, why we have to do a set of ladder diagrams. Before I go ahead, I just wanted to maybe clarify one thing that probably I did a mistake last time, just a simple qualification. So on Friday, I told you about this reparameterization invariance, so I just wanted to make my statement correct, that the correct transformation for this field under reparameterization is accounting for this phase factor. Probably I missed this phase factor last time. And the way one can understand this phase factor is when I wrote into large and small components, the HV is defined as is this, and then when you do V to V mu plus epsilon mu by M, you can see clearly that there has to be a phase factor corresponding to this term from this exponential. Okay, just wanted to make things clear because I will put up the notes and you might see this coming in the notes. Okay, so let me maybe make a group of 3 or 4 students. So 6, 9, 12, 18. So roughly there are about 25 students. I would put people in groups of 2 or 3 together, 3 to 4 together. And so one of the problems that we first will study is using power counting in non-relativistic QED to look at problems why there is why bound state would require summing up several diagrams. So for example, the diagram that I'm trying to look for is this. So let's say this is generated from some E plus E minus. We are not looking at the process right now, but my goal is to show that is this one loop all contributing at, is contributing at the same level as the tree level in power counting of NRQED when there is, we are trying to study bound state systems of positronium, okay? So let me just recall what are the Feynman rules and what were the scaling dimensions for the power counting. So let me just first tell you what is the final result. What you will find is that both this contributes at order alpha square by V. This also contributes at order alpha square by V for bound states. Which means alpha S is of order V. Yeah. I'm sorry. I'm sorry, really sorry. Yeah, I'm sorry. Yeah, so this relation between the alpha and V is only holding for the bound state situation. We explicitly showed it using the virial theorem, or even Professor Rishi showed it today also. In general, if you do not study bound state problem, there is no reason V has to be of order alpha, okay? only for bound state problem, V is of order alpha, and that is where this important point enters, that all these one loop exchange or two loop exchange will contribute at the same order at the tree level. So just to recall again the power counting was momentum is MQV, energy is MQV square, and so let me write the let me consider this. So let me consider the diagram here now. So let us say this is coming from this virtual photon, which has some center of mass energy, zero momentum. Let me write it big. And then yeah, so let me make it bigger diagram. Let me just write the momentum, and then I'll leave it up to you to figure out how for bound state it is at the order of alpha V square. So there will be another analogous expression with minus E center of mass plus P0 and P. This momentum is P minus Q. This is Q minus K. This is E center of mass over 2 plus Q. And this is minus E center of mass over 2 plus Q. And okay, so depending upon the K, this will have some specific momentum like minus E center of mass by 2 plus K. And this will have E center of mass by 2 plus K. So we'll only look at this one loop structure here, not go anything beyond it. Things to note. So E center of mass is roughly twice of MQ because I'm creating this pair of E plus E minus, so which is my generated by these lines here. EQ minus MQ is again at the order of MQB square. And for the momentum loop, take Q0, P0 to be of order MV square. MQB. Okay. So everybody know what is the propagator? You have to so take these scaling rules and start from the QCD propagator for the heavy quark. Try to find what is the scaling. I mean, I'm not asking you to do any calculations, okay? I'm just asking you to use the power counting and see what is the result you are getting. So maybe sit together with cup and try to figure out. I mean, I'll leave it up to you. It will be better. I mean, this is the tutorial. Otherwise, I will try to, I mean, I'll wait for 10, 15 minutes and then try to cover it. So just to give you the hint where to start with, the propagator that you will start is, let's say this one, which is given by E center of mass by 2 slash minus M, and which you will write it as E center of mass by 2 gamma 0 plus Q0 gamma 0 minus U dot gamma plus MQ divided by So please work out the scaling dimensions here and let me know what is the answer you are getting. So insert the powers of V there and tell me what is the leading order term. Yeah, because this is in the QED, this is in the QED sector now. Yeah. I want to show in the QED sector first that why all these diagrams have to be sound. Is everybody clear what has to be done? So I have already given you the scaling dimensions or the power counting. This is one of the propagators that you see will enter here in the loop. Use these V scalings and like let's work for 5 minutes, let's say, and tell me what is the leading order term that you are getting. Okay? This is the question to start with. So yeah, I would suggest people to group together and work because that is how you will learn better. So again, you are not evaluating anything. You are just substituting the V scalings and seeing what is the leading order in V you are getting. That's the question that I aim to ask. Again, don't do any computations. Okay. Just to tell you, E center of mass. Not just yeah. Yeah, just. Oh, I should have given one more. Sorry, I should have given one more thing. Yeah, okay, go ahead. So to make life simpler, just to give another hint, I would define energy E, which will basically subtract my 2mq factor. So E center of mass by 2 minus mq, because if I do this, then my E scales as mqv square, which is what I have written here. Okay. So just to put you on right track, basically. Sorry?
Q0 is mv square or mqv square?
Q0 is mqv square. It's P0. This P0 is energy. P0. The 4 vector P is P0 and momentum is 3 vector. This is energy here. Okay, so let me give the answer because I have to cover another topic also. So if you do the counting, what you get is I times 1 plus gamma 0 by 2 E by 2 plus Q0 as this as the leading term in the V expansion. And the point is, how did I arrive at this? So let us look at the numerator. If I use this relation, which means my E center of mass is E plus 2mq, which I will substitute it for the simplification. This numerator term goes like E by 2 gamma 0 plus mq gamma 0 plus 1 plus q0 gamma 0 minus q dot gamma. So let us compute the power scaling in V. Can everybody see the blue color? Is it clear? Okay. This first term is V square because my energy is, let's do the counting in terms of V. This is V square. This is order 1 in V, okay? This is just MQ term, this is order 1. This is order V square, and this is order V. Is is steps. Clear? I'm not doing any computation. I'm just putting the scaling in terms of V. That's it. Which means out of all of this term, really, this is the leading order term that will contribute to my calculations. Okay? So this is roughly MQ1 plus gamma 0 plus something at order V that at present I'm not very much worried about. Then, okay, there is no other color. So now let us look at the denominator. The denominator is E square by 4 plus Q0 square plus E Q0 plus EMQ, sorry, plus 2MQ Q0 minus Q square. This is V raised to 4, okay? This is again V raised to 4, because Q0 is V square. This is V raised to 4. This is V square. This is V square. And this is V square. Clear? Again, no, yeah.
The Q is ordered B.
So
This is a loop momentum, let's say the photon momentum.
you need, if you take it to be a very hard scale, then it is not, you're not looking at bound state problem really. For the bound state, you need to integrate out.
That doesn't fall back.
Yeah, that does not fall from. You have to assume like a potential gluons. I did not wanted to use the term. It's something called as the potential.
Soft, right? Or B.
No, the Q0 is, so Q0 is V, but the momentum is MV. It's something called as potential gluons in, you are not exchanging hard gluons, you are exchanging something called as potential gluons. Photons, I'm sorry, photons. Yeah, potential photons, and that is the reason we have to use this. Yeah, scaling of Q0 and Q have to be assumed here. It's not. No, it's called potential gluons. It's not soft. So soft or soft photons basically means scaling with energy and momentum scaling with V. Ultra soft means scaling with V square. But this you see the energy scales with V square, but the momentum scales with V. So this is something called as potential photons. Because the photon is not on shell here. The potential photons are not on shells. Okay. So the scalings is really V square and V. I mean, this maybe this would. So the ultra soft photons don't give me, no, it's not the power counting. The question is for formation of bound state, which is the photon that is contributing to the bound state really. So ultra short photons will not contribute. They are too low of a scale. In my EFT, which is at MV square, there would be ultra short photons. In order to get the bound state, I have to integrate out the momentum associated with the heavy quark, which is MV, and also energy, which means in some ways introducing this MV square term. No, this is not an assumption. I mean, this is something called as method of regions. You will find it in textbooks like SCAT or something where they do it more rigorously. Exactly.
Specific configurations that give rise to different effects.
Yeah.
Like all the modes that come with this particular scaling give rise to the desired
potential. This is the point. I mean, that would be kind of a little bit beyond the scope of what we are trying to do here.
So if you go back to the last two, when Neuberg talked about skate, in those lecture notes, which are YouTube and various, you will find this region of integration by regions and how the different modes are separated out. that might be a good reference.
To study. Okay. So again, what you find here is that only these pieces are contributing to my case. And if I take the order, if I only keep these terms, that will basically give me this propagator or the expression of this propagator. Okay. This is the simplest thing that I did. Now, in the loop calculations, what you would find is that so let me just quickly write the loop expression. The loop expression is some g raised to 4. I will not worry about factors of I, so don't, I leave it up to you to figure it out. D4Q, sorry, maybe let me use the, so I will have one propagator here, one propagator here. I mean, all of these contributing together. So this is some I by, yeah, I'm basically looking at this part. E by 2 plus Q0 minus Q square over, oops, sorry, I'm really sorry. You will have another propagator from this side, which is E by 2 minus Q0 minus Q square over 2MQ plus I epsilon naught. I'm looking at longitudinal photon exchange. The transverse ones won't contribute here because they are kind of suppressed in the power counting coming from AI. And now if you vaguely write this expression, this would be proportional to some g raised to 4 d3 cube by 2 pi cube 1 by E minus Q square by M cube 1 by P minus Q square and 1 by Q minus K square. These are all 3 momenta. These are not 4 momenta. I have basically integrated out over Q0 using one of the poles here. That is how I simplify my results. And this we already have seen from the power counting now. So this basically scales so this term scales as 1 by V square, so V raised to minus 2. This scales as V raised to minus 2. This scales as V raised to minus 2. My momentum scales as V cube. So what I get is G raised to 4 by V cube. Okay? So I am basically only looking at this one loop. Okay? I write the propagator, I write the expression, simplify the Q0 integral, arrived it here. We just now looked at how we arrived at this point. Because of energy, it scales as 1 by V square. Because of momentum, it scales as 1 by V square. This scales as 1 by V square. G raised to 4 are the 4 couplings in front of this. And so this overall scales as G4 alpha V by V cube, which is really alpha square by V cube, which you write it as alpha S by V square times alpha S by V. Okay? Is anything unclear? Please let me know. Yeah. So the point is at the tree levels, yeah, ideally there would be things like that. But the point is, this is my first exchange. Yes? This is already the piece that is appearing up in this side. Now the second exchange is, the second exchange is exchanging 2 gluons. And so that's why I'm specifically focusing on this one loop diagram. Okay, that's the point I wanted to separate. Because this part is already appearing up here. Okay, it's the same thing in both sides. Now here you immediately find that for my bound state problem, I've already shown that alpha S is of order V, which means this is really alpha S by V square for alpha S of order V. And this is only true for the bound state problem. In reality, alpha S and the velocity might not be related with each other. It's only when we have a bound state problem using virial theorem, or like Professor Rishi mentioned, we can show that alpha S is of order V. And if you compute the tree level diagram, now answering back to your question, if you compute really the tree level diagram of, if you just compute this tree level diagram, this is really G square over some momentum exchange, P minus Q square or P minus K square. And this is alpha S over V square. Okay? So as you see at one loop and tree level, they are both contributing at the same order in the case of the bound state problem. And this is the reason why really for bound states, I need to have to sum all over these longitudinal gluons. So there are really, these are called ladder set of diagrams because it looks like a ladder here if you rotate from horizontally to vertically. So this is the reason why for the bound state problem, I have to look at all these Coulomb resummation diagrams, which is termed as ladder diagrams. It is not very trivial to show how this resummation amounts to solving Schrodinger equation, but generally, I mean, I will have to look back into the literature how to prove that. But in general, this resummation of diagrams is kind of equivalent to like summing this T matrix at all orders. Like in non-relativistic sense, you have this T matrix written as V plus V G0 T. And so this is what you are solving in some way. You are resumming all set of diagrams here. In simple analogy, you saw in cold atoms that when we had unnatural scattering length, we had to sum all these bubble diagrams because diagrams at loop order were contributing at similar order or higher. And so this is kind of a similar story. It's just that the bindings are, the analogy is the resummations, but the way the bound state forms is a different physics. Yeah, which one is the two loop? So so if I just focus on this part, this is one loop. If I just focus on this one exchange, this is tree. I mean, if you account for this, then you will say that, oh, this is also two loop. Yeah, I mean, I'm removing out this part. I'm looking at only this piece and then this piece. That's what I'm saying, tree and one loop in that respect. No, this is hydrogen atom. So that is the thing. There, the physics was of unnatural length scale. And so the binding was controlled by the scattering length. The binding energy was small because of the A being large. Here, it's a different physics. It's not coming from unnaturally large scattering length. It is coming from exchange of these potential gluons. And so the binding energy has no direct relation to scattering length in a way. This has nothing to do, this is like a hydrogen atom system now. Okay, so the other exercise in whatever 20 minutes that I have time left, because this will be covered by Professor Rishi in the next lecture, is we will look at heavy quark field normalizations, because in the next set of lecture, he will discuss about heavy light current or maybe heavy current together, which will involve these one loop diagrams. So let me just erase and so whatever I explained works perfectly well for JSI also. Okay? You replace the electron with charm, anti-charm, it's the same argument. So yeah. G4, yeah, alpha square over V cube. Yeah. Yeah.
Now essentially the alpha squared thing now looks like it's at alpha s, so just like it should be for the 1 to case. But we can also eliminate the alpha s completely.
Yeah, I mean alpha S and V in case of bound state is a complementary variable. You can eliminate one in terms of other. It is just to, yeah, it is just to explain, like you see the alpha is associated with this fine structure constant. but alpha is of order V. I mean, you can eliminate and say that this is really 1 by V.
I mean, it's just to like,
Yeah, it's
there's
just,
other meaning.
yeah, no, there's no deep meaning to it. I mean. The full resummation, that would be equivalent to like they solve it. I don't have an answer, good answer to it right now. Okay, I mean, generally this resummation is some ways equivalent to summing up all these T matrix elements. I'm not aware how to do it, but they connect it to solving it to Schrodinger equation finally, written in terms of the T matrix. I mean, the goal was not to do the loop computation at all. The goal was to just show that how even at one loop where you expect some suppression for bound state, you do not see that. You see the same contribution happening at tree. Probably some might have. I have to look at literature. I'm not aware. The question is, how do you compute these ladder diagrams in full?
This is nothing but what some of you may have seen in dark matter study.
Goes by the name of? Yeah, Sommerfeld enhancement. Okay. I mean, in cold atom case, you saw that, or Professor Kaplan mentioned that, yeah, this was this plus this, yes, this was IT and this was IT. You have to do something similar here, but I am not an expert that can, I can find the literature, but cannot. Okay, so now the goal is to look at something called as the heavy quark field renormalization. So I'm coming back to HQT. Let me motivate why we are doing it. On Thursday lecture, as Professor Rishi will tell, we will do some composite operator calculation, which is the heavy light current. It's a composite operator made of heavy field and the light field. So if you have a field composite operator made of psi bar, gamma, psi, I'm not worried about what gamma is right now. It's just a composite field for me. In the renormalized perturbation theory of QFT, you define something called as the renormalized field Z psi with normalization of with this wave function renormalization factor. Okay, we will compute something analogous here for the heavy quark field, and the point is this renormalized operator or this O would be written as this. Okay, nothing else. And basically, as you know, this composite operator is psi bar gamma psi for me, which is basically Z psi over Z0, psi renormalized gamma psi renormalized. And for this operator to be renormalized, I would define something called as psi bar gamma psi r plus Z psi minus Z0 minus 1, where this would be my counter term that would cancel off the divergence. Wait, did I do something wrong? No. Yeah. And this would be my operator. It's clear. Yes. And so we will see one application of this when we are computing heavy current or heavy light current, as will be discussed on Thursday. So in reality, to compute this Z0 factor of, or to compute this anomalous dimension for this coupling, for this associated with Z0, you really need to know also this Z psi, yes, from the counter term. Once you know Z psi, then you can compute what is Z0 is. So we will see the application of that Thursday. Today we will do the Z psi computation for the heavy quark EFT. So I start with my heavy quark EFT Lagrangian, which is, so let me directly define the Lagrangian in static limits. So for simplification, let me go to MQ tending to infinite limit and only worry about the static, worry about the leading term. So H bar nu R I V dot D H V R. Yeah, yes. Oh, let's make it del. Timing. It's ZH minus 1 HVR I V dot del HVR. So this will define my counter term to cut the ZH. And as I already told you, what was the relation I showed? Yeah, that HV is ZH HVR, 1/2. So the diagrams that we are trying to compute here are these one loop diagrams in HQET. Where this is proportional to I V dot P ZH minus 1, my counter term piece here. And this is my heavy quark going in, so with I, P, so J, Q, this is P minus Q, and this is, yeah, so this is the spin index that I'm trying to write, this is P, this is the momentum. It will get clear why I have written I, J, and K there. Just give me a minute. So this is the one loop HQET self energy. And the goal is to compute this diagram in HQET. By the way, just to, if anybody wants to look at the reference for the time being, all of this part that I'm discussing is mentioned in heavy quark physics. By Manohar and Weiss. This is, I think, chapter 3 or 3.1 or something. Just look at the book and you will find most of the things discussed there. Okay, so let's write this diagram for our purpose. So yeah, just let me rewrite again. So momentum coming in, P minus Q, E, K, J. Okay, so everybody recall the this heavy quark EFT Feynman rule. Just to recall that the vertices goes like some proportional to G times TA Ij V mu. Okay. Yeah, I mean there will be some factors of I or negative sign missing, but that's not my goal right now. But this is somewhat the proportionality. Here, I and J are, sorry, colors, is what my. So I'll just use the Feynman rule now. The propagator here moves like I by P dot K plus I epsilon naught, is the K. And so let's write down the diagram. So this diagram is proportional to, yeah, the color matrices, color matrices. I may have said wrong. So this is color matrices. This is HQET. I mean, yeah, QED also. I mean, basically the color matrices is going to give you a constant factor that's will be pulled out. So this diagram will be proportional to some, yeah. So TA IJ, again, let's do the A. TAJK, G square TDQ by 2 pi 4, V mu I by P minus Q dot V plus I epsilon naught. And V mu I by Q square plus I epsilon naught. So I'm using Feynman gauge for the photon for this. Yeah. Yeah, okay. So KJ and JI. Yeah. Yeah, thanks. Sorry. Yeah, basically the point is that this together will give me some KI. Yeah. And this is my factor of CF with delta KI, where CF is 4/3. So this is the part of the color. The color will only give me a 4/3 factor. That is a constant factor. In QED, you won't have similar things. So this is my propagator here. Yeah, this is the V mu vertex coming from here. This is the V mu coming from here. And this is the gluon propagator in Feynman gauge. So the goal is to compute the counter term. So how do we extract the counter term in QFT? The way we extract the counter term is we look for 1 by epsilon poles, yes, that to cancel the 1 by epsilon poles. And so my goal would be to extract the UV part of this diagram, so extracting the 1 by epsilon pole. And obviously there would be some finite piece, which I'm not interested right now. So in order to extract the UV pole, let me use the trick that I will introduce a IR regulator for the photon mass, or IR regulator for the photon propagator. So sorry, photon slash gluon, which is basically defining 1 by Q square minus M square plus I epsilon naught. And finally, taking, so IR regulator, M square tending to 0. Okay, so this M square has been introduced so that I can control my IR divergence, because my only interest is to compute 1 by epsilon terms. I'm not interested in the finite term right now. So let me erase this part. I mean, no, this is Q square here. Yeah. This is 1 by Q square. But it's not sitting inside the gluon propagator, yes? Just 1 over Q square. And so, so how do one simplify this thing is, there is an identity that is mentioned, that is something analogous to this Feynman, this parameterization X that we introduce. I forget the name here, that we do in relativistic theory. So you use the relation that 1 by AR BS. I will define what this AR and BS is. 2 raised to S gamma R plus S divided by gamma R, gamma S, dx 0 to infinity 2bx R plus S. So in my integral, the A is q square minus m square, B is P minus Q dot V, R is 1 and S is 1, okay? So this is this that, I mean, I think in relativistic theory, we introduced this X where this integral goes from 0 to 1, if I remember correctly. But here is a different identity similar to it. So if you use this thing, then basically your integral simplifies to something like, again, I'll not too much worried about the factors here. So minus 2CF, so which is 4/3 factor coming from the CF here. So note that this CF is just the Casimir operator. This has nothing to do with the CF that appears up in the Fermi term. So I'll just write 4/3, keep reminding. G square mu raised to minus 2 epsilon, pi raised to 2 minus epsilon, 2 pi, 4 minus 2 epsilon, gamma epsilon, dx 0 to infinity x square minus 2x p dot v plus m square. So I have used, to arrive at this point, I have used dimreg, okay? So after I simplify, use this identity, use the dimreg over, I have to use the dimreg over ddq. This is the result that we will end up getting where only x integration is left. So after dimreg, so more details will be in the notes, but here I don't want to go into that part. Now, the point is that this integral as such is divergent for epsilon 0. If you take epsilon tending to 0, this integral will be divergent. So in order to compute this integral, we have to keep the epsilon finite and then analytically continue to epsilon tending to 0. In order to do that, again, there's a cute identity that is introduced. So again, these all details are in this book, Heavy Quark Physics, is let us say there is this integral depending on A, B, and C, which is given by dx 0 to infinity x. Oh, sorry. So here A is corresponding to minus epsilon, B is corresponding to P dot V, and C is m square. This integral can be simplified using the fact that d by dx I of ABC is proportional to 1 by 2a let me see, C minus B square. Sorry? I think it is d by dx. Yeah. Because, yeah, I is the integrand. Yeah, I is the integrand. I is this integrand. Yeah. So I prime, let's say. I prime is this, sorry. Yeah, sorry for this stupidity. Okay, I should have maybe. Yeah, okay. No, okay, so maybe let me write it correctly. Sorry, I did it wrong. Yeah, sorry, this is the identity. It's not just the integrand is multiplied by x plus b. Okay, so you use this because this would imply that this IABC, so really this integral, if you use this identity, would go down as 1 by 2, 1 plus 2a, x plus b, x square plus 2bx plus c raised to a, 0 to infinity, plus 2a c minus b square I, a minus 1, b, and c. So I have not done anything else. I have used the integration by parts here because this is my integrand that appears up in my integral. And I just express this as this total integral plus this term and then divided by 1 by 2a. This is the identity that is allowing me to exploit that. So this piece is this. So if you do all of this and use the relation, what you really get is a finite term from this integral. I'll just write the results now here, which is minus mu raised to 2 epsilon, 1 minus 2 epsilon, minus p dot v, m square minus epsilon, minus 2 epsilon, plus order epsilon terms. I'm not interested in writing order epsilon term because eventually I'm taking epsilon tending to 0. So all those terms are 0 form. And if I take epsilon tending to 0, you see that eventually this term will give me a finite piece. This is 1. And this is how we extract. Yeah, this is how we will extract the divergence now. So let me see if I did some, yeah. And the divergence will come from expanding this gamma factor. So, yeah, I made a stupid mistake. So you have this piece as it is. Then what you are getting is something like a finite piece, which is mu raised to 2 epsilon by 1 minus 2 epsilon minus p dot p raised to. So this piece is there. 1 by epsilon will come from here. And finally, the result is that the self energy is minus I CF over 2 g square mu minus 2 epsilon by 4 pi square p dot p divided by epsilon plus finite terms in epsilon. So this is my 1 by epsilon pole that I was trying to look for. Okay, the whole game I played was to do this. And this, again, this 1 by epsilon is coming from this gamma epsilon here. Okay, and this integral gives me a finite piece in epsilon. So now, once you extract the epsilon pole, we already know what the counter term right now is. And so the counter term is ZH. We had defined ZH minus 1, which should be canceling this thing. So let me call it X plus X is 0. And so this is basically ZH is 1 plus my terms. So CF by 2 mu raised to minus 2 epsilon alpha S by pi epsilon. So this is my wave function denormalization factor. On Thursday, Professor Rishi will continue from here and use this relation to do the heavy light current or heavy current and compute like anomalous dimensions for associated to this composite operator. Okay. I mean, you mean the 1/4 pi, on the 4 pi square suppression? This I'll have to check. I don't have memory of it. I mean, one will have to carefully look at it, I would say.
Square by 4 pi.
Yeah, alpha is g square by 4 pi. Will ha-
That's the 4 pi.
Yeah.
Yeah, yeah. The G square is the coupling constant and
Yeah,
4 pi.
there is 4 pi. Yeah, okay, good. Yeah. So this ends my tutorial. On Thursday, after Professor Rishi has gone over the heavy light current, we might try to do some other calculations like anomalous dimension of CF, but try to.
This is the last one by Abhishek.
Yeah.
5 hours of